Hey there. You know those redox reaction problems in chemistry that can sometimes feel, well, a little impossible? Today, we're going to crack one wide open. We're going to tackle a common exercise, break it down piece by piece, and by the end of this, you'll see them in a whole new light. So here it is. This is our target. Concept Assessment Exercise 2.1. The mission is pretty clear. We need to figure out which atoms are gaining electrons and which are losing them in these three reactions. And the way we're going to do that is by using the oxidation number method. You ready? Let's do this. Okay, so here's our game plan. It's really just two simple steps. First, we need to get our toolkit ready, and that means understanding oxidation numbers. Then, once we've got the tools, we're going to apply them and solve each of these three reactions one by one. Before we can crack any codes, we need the key, right? And for redox reactions, that key is definitely the oxidation number. Just think of it like bookkeeping for electrons. It's a way to keep track of where they are and where they're going during a reaction. So, the official definition is that it's the apparent charge an atom would have. Now, it's not always a real charge, but it's an incredibly clever system that lets us follow the electrons. And that electron transfer, that's the heart and soul of what a redox reaction is all about. The great news is, you don't have to guess these numbers. There's a set of rules, kind of like shortcuts. For instance, any element all by itself, like a chunk of iron or oxygen gas, is always zero. Easy. Some elements are super predictable, like group 1 metals are always +1 in a compound. Oxygen is almost always a -2, and hydrogen is usually a +1. And the most important rule of all the numbers in a neutral compound have to add up to 0. That's the one that lets us solve for the tricky ones. And here it is. This is the whole point. If you see an atom's oxidation number go up, it's been oxidized. Think about it. It lost negative electrons, so its charge goes up. If the number goes down, it's been reduced, meaning it has gained those negative electrons. So increase is oxidation, decrease is reduction. That's the core concept right there. All right, our toolkit is ready. We've got our rules. We know what we're looking for. It is time to put this into practice. Let's jump into the very first reaction from our exercise. Okay, here's our first patient on the operating table. We've got chlorine gas reacting with sodium hydroxide. It looks a little busy, I know, but trust the process. Let's start assigning those numbers and see what the story is. Let's just apply our rules. Chlorine gas, Cl2, is an element, so it starts at 0. Now look at the products on the right. In sodium chloride, NaCl, the chlorine is -1. But look at the next one, NaClO. We know sodium is +1 and oxygen is -2. For that whole thing to be neutral, that chlorine has to be +1. So wait a minute, chlorine went from 0 to both -1 and +1 in the same reaction. So what in the world happened here? Well, chlorine started at 0 and its number went up to +1. That's oxidation. At the exact same time, it went down from 0 to -1, and that's reduction. When a single element is both oxidized and reduced in the same reaction, that's a special case called a disproportionation reaction. It's actually a super important process. It's how chlorine works its magic in swimming pools. How cool is that? Puzzle number 1 solved. Okay, on to our second reaction. And this is one you have seen thousands of times, probably without even thinking about the chemistry. This is simply the formation of rust. Now, this one is much more straightforward. Iron and oxygen both start out as pure elements, so their oxidation numbers are 0. Done. Now let's look at the product, iron 3 oxide. We know each of those 3 oxygens is a -2, so that's a total negative of -6. Since the whole compound is neutral, the 2 iron atoms together have to be +6 to balance it out. So if 2 irons are +6, each one must be +3. And there's our answer, clear as day. Iron went from 0 all the way up to +3, so it got oxidized. Oxygen went from 0 down to -2, so it got reduced. It's that simple. Every time you see a rusty nail, you're looking at the result of iron being oxidized. 2 down, 1 to go. Okay, here we go, the grand finale. Glucose plus oxygen gives you carbon dioxide and water. This isn't just some random equation, this is cellular respiration. This reaction is happening in your body right now, and it's the fundamental reason you can move and think. Let's see how the electrons are flowing. Okay, let's break this one down. Oxygen gas, O2, is easy. It starts at 0. Now for glucose. We know hydrogen is +1 and oxygen is -2. So with 12 hydrogens, that's +12. With 6 oxygens, that's -12. Well, +12 and -12 cancel each other out perfectly, which means the 6 carbon atoms must have a collective oxidation state of 0. So on average, each carbon is starting at 0. Now look at the product, CO2. Each oxygen is -2, so to make the molecule neutral, that carbon has to be +4. And that's the whole story right there. Carbon's oxidation number skyrocketed from an average of 0 all the way to +4. That's a huge oxidation. And at the same time, oxygen went from 0 down to -2, getting reduced. It's this exact transfer of electrons from carbon to oxygen that releases the massive amount of energy that powers, well, us. So there we go, we've solved the entire exercise. But this is so much bigger than just getting the right answer on a problem set. You've just picked up a new kind of superpower, a new way of seeing the chemical world. I mean, really, why do we care about tracking these imaginary charges on atoms? What's the point? What does this actually do for us? It matters because you can now see the invisible. You can see the flow of electrons that powers our world. It's the engine running inside the battery that's powering the device you're watching this on. It's the process that makes a car rust. And it's literally how your body turns your last meal into the energy for your next breath. By cracking the code of oxidation numbers, you've learned to read the fundamental electric current of technology and life itself. The only question is, what will you see differently now? We're going to dive into something that can feel a bit tricky in chemistry, balancing redox equations. But don't you worry, because we are going to crack the code with a powerful method that turns these complex puzzles into something you can totally solve. So take a look at this. We've got copper reacting with nitric acid. Now, if you try to balance this the old-fashioned way, just by counting atoms, well, you're going to find yourself going in circles pretty fast. And why is that? It's because electrons are on the move here, and to keep track of them, we need a special kind of tool. So here's our game plan for today. First, we'll get to know the method itself. Then we're going to walk through 2 different examples, step by step. And finally, we'll boil it all down into a simple blueprint that you can use for pretty much any redox equation out there. All right, let's open up our toolkit. The main tool we're going to be using is called the oxidation number method. Just think of it as your reliable, step-by-step guide for untangling even the messiest looking reactions. This whole method is built on one simple, fundamental rule of nature. You can't just lose electrons into thin air. In any of these reactions, the number of electrons lost by one thing has to be perfectly equal to the number of electrons gained by another. It's a perfect exchange. Our job is just to make the equation show that beautiful balance. And here's how we're going to do it. With these 5 steps. This is a pretty standard process. We'll assign numbers to track the electrons, figure out who's gaining and who's losing, calculate how many electrons are moving, equalize the whole exchange, and then just do a final cleanup. Ready to see it in action? Let's do it. Okay, it's time to solve that first puzzle. We're going to apply our 5-step method to this reaction, the one that produces nitric oxide, or NO. So here's our equation again. First things first, we have to assign an oxidation number to every single atom. Think of this number as just a way to do some bookkeeping for the electrons. We follow a few simple rules. Any pure element, like our copper here, is always 0. Oxygen is usually a -2, and hydrogen is a +1. And from there, we can figure out all the rest. So after we've put a number on every single atom, we just scan across the equation and see who changed. And look at that, 2 elements really pop out. Copper starts at 0 and ends up at +2. At the same time, some of that nitrogen starts at +5 and ends up at +2. We've found our main players. Okay, let's zoom in on those changes. Copper's number went up from 0 to +2. That means it lost 2 electrons. That's what we call oxidation. Meanwhile, nitrogen's number went down from +5 to +2, which means it gained 3 electrons, and that's reduction. But hang on a second. 2 electrons lost does not equal 3 electrons gained. Something's not right. To fix this, we need to find the lowest common multiple of 2 and 3. And that number, of course, is 6. 6 is our magic number. It's the target for both the electrons lost and the electrons gained. So this is the crucial moment. To get to 6 electrons, we need that copper reaction to happen 3 times, and we need the nitrogen reaction to happen twice. These multipliers, 3 and 2, are literally the keys to balancing this whole thing. Now, we just take those multipliers, 3 and 2, and we pop them into the equation as coefficients in front of the molecules that are doing the electron swap. This gives us 3 coppers and 2 nitric oxides. But hold on, we're not done yet. This is a big step, but we've only balanced the electron transfer. Now we got to balance the rest of the atoms. And this is the final step, the home stretch. We just balance by inspection. So on the right side, we've got 3 copper nitrates, which have 6 nitrogen atoms in them, plus the 2 nitrogens in nitric oxide. That's 8 nitrogens total. So we need 8 nitric acids on the left. That gives us 8 hydrogens, so we need 4 water molecules on the right. And let's do a quick oxygen check. 24 on the left and 24 on the right. Perfect balance. We did it. Fantastic. Okay, to really make sure this method sticks, let's run through one more example. We're going to use the exact same starting materials, but we'll change just one of the products and see what happens. Here's our new puzzle. It looks almost identical, right? But this time, the reaction makes nitrogen dioxide. That's NO2. Does that one extra oxygen atom really make a difference? Oh, you bet it does. Let's find out how. All right, once again, step 1 is to lay out all our oxidation numbers. Most of them are exactly the same as before. But check out the nitrogen in NO2. Since each oxygen is -2, the nitrogen here has to be +4. That's a totally different number, which means we have a different puzzle to solve. So what are the changes this time? Well, copper is doing the exact same thing it did before. It's losing 2 electrons. But nitrogen, this time it's only going from +5 down to +4. It's only gaining a single electron, not 3. This is a whole new ballgame. You know what though? Balancing the electrons here is actually way simpler. Copper loses 2 electrons and nitrogen gains 1. So the lowest common multiple is just 2. Our target is a 2 electron transfer. Easy enough. So what does that mean? It means we just need to multiply the nitrogen part by 2, which gives us 2 NO2 molecules. And that means we only need 1 copper atom. Now we just balance the rest by inspection. We've got 2 nitrogens in the copper nitrate, plus the 2 in nitrogen dioxide. That's 4 on the right, so we need 4 nitric acids on the left. That gives us 4 hydrogens, which means 2 waters on the right. And boom, balanced. See how the method just works? All right, let's zoom out for a second and just summarize what we've learned here. We've taken two really complex-looking reactions and we've systematically broken them down and solved them. And this slide right here really says it all. I mean, look at them side by side. The only difference in what was being made was NO versus NO2. But that tiny one-atom change completely rewrote the recipe for the reaction. The first one needed 3 coppers and 8 acids. The second, only 1 copper and 4 acids. That's amazing. So here it is. This is your blueprint. These are the 5 steps you can take with you to solve any redox equation that gets thrown your way. Assign, identify, calculate, equalize, and inspect. You just follow these steps and you really can't go wrong. So now you have this really powerful, logical tool in your chemistry toolkit. The next time you see a crazy-looking redox equation that seems impossible to balance, you'll know exactly what to do. Thanks so much for watching.